So in this section, we're going to take a look at how we can use limit statements to help us define or analyze continuity for a graph. And we're going to take a look at this very drastic piecewise function here with many different things going on, like holes, jumps, and asymptotes. And we're going to fill out the table below. And once we do that, we're going to go ahead and write some pieces of information that we can kind of pick apart and analyze from the table. So we'll do like the first 2 or 3 together, and then I'd like you to pause the video and try to do the remaining on your own. So we're going to take a look at the first value here at -6, and the first question is asking us, is the function defined at that spot? Meaning, do we have a closed circle or a graph at that location? So if we go to -6 on the x-axis and up to their graph, we have an open circle, so it is not defined there. Okay, there's no closed point or graph at that location. But then we can start taking a look at limits, like the left-hand side, the right-hand side, and then therefore the overall limit. So if we were to approach -6 from the left, we would approach the hole, which has a height of 5. If we were to approach from the right-hand side, we would also approach the hole, which has a height of 5. So if the left side and the right side approach the same height, then the overall limit happens to be that height as well. The last question is asking us, is the graph continuous at that spot? Meaning, can you draw the graph without lifting up your pencil? No holes, no jumps, no asymptotes. Well, if we take a look at -6, we clearly have a hole, so the graph is not continuous there. So we're just going to go ahead and take a look at these other locations. For instance, -3, is the function defined at that spot? Yes, we do have a closed circle or a graph somewhere. If we approach from the left, we approach a height of 2. If we approach from the right, we have a height of -4. So does the overall limit exist? No, because notice how the left and the right don't match. And then is g of x continuous at that spot? No, we'll say because we have a jump. Let's take a look at 0. The x value of 0 is right here. So we do have a portion of a graph there, or a closed circle. If we approach from the left, we have a height of -1. From the right, another height of -1. The left and the right side match, so the overall limit exists. And is it continuous at that spot? Do we have a hole, a jump, or an asymptote? The answer is no. So yes, it would be continuous. So I want you to go ahead and try the next ones for 2, 6, and 8. I'll jot those down real quickly, but make sure that you can get the same results. Alright, so taking a look at the rest of them, I did forget to write in the actual value if we had a point defined there. So go ahead and write those down. It looks like at 2, we have a vertical asymptote, at 6 we had a jump, and at 8 we had a hole. So if you take a look at our results from this table, we want to come across or think of like 3 things that would make a function have a continuous portion or a continuous graph at a particular spot. So notice how the only one that we said was continuous was this x value of 0. So what do you notice about the information that we have for that location versus the other ones that we did? Well, if you pay really, really close attention to the numbers, notice how we did have a point exist and its value was -1. We did have a limit exist and its value was -1 as well. So it looks like the point and the limit both have the same value or the same height or the same location. For some other ones, notice how we had a limit value of 5, but we did not have a point there, so that's resulting in a hole. Same thing down here, we did have a limit value, but it did not match the point value, so there was another hole. Sometimes if we have a jump, the point and one-sided limits might match, but notice how the overall limit did not match because the right-hand side was not 2 like the other ones. So it looks like in order for us to say that a graph is definitely continuous, the point location and the overall limit value must be the same. So we have to kind of make sure that we have this information available to us. We're going to say one thing is that G of A is defined, meaning we have a point existing. So we must have a closed circle somewhere in order for you to be continuous. If you don't have a closed circle, you might have a hole or a jump. So a point is definitely one stipulation. Something else we must have is the limit existing. So the limit exists. Notice how this is an overall limit, so the left and the right side must match each other. So we must have a point and we must have a limit. The kicker, notice from the table, is that they have to match each other. So just having a point is not enough, and just having a limit is not enough. The point and the limit must match. So we can say G of A must equal the limit. Okay, so the point exists, the limit exists, and the point and the limit match. This is going to be our definition of continuity, and I think I like to use kind of an example here. Most of us are drivers or will be getting our driver's license soon if you don't have it. So I want you to think about driving across a river, and in order for you to cross a river, we have to have a bridge. And in order for you to continually drive, okay, without having to stop or do anything, the bridge and the road must match up. So I think this is a good visual for us to kind of understand what continuity means. I want you to think about the bridge as the point, and the road is like the limit. Notice how in this first example with crossing our river, the point exists, so we have a bridge, but the limit does not exist. Notice how the left side of the road does not meet up with the right side of the road. In our next example, we have the limit existing, okay, so the left side and the right side of the road meet up with each other, and the point existing, so that's qualifying statements 1 and 2 on our paper. Okay, so the point exists and the limit exists, but notice how the point and the limit do not match, meaning the road and the bridge are not connected. The only way you can continually drive is if the point exists, the limit exists, and they happen to match up perfectly at the same location. So I think this is a good visual for us to have. So these 3 rules are really important, 1, 2, and 3 at the top of the page, and you might hear me refer to these. I'm going to write this down at the bottom. This is what I call the Holy Trinity of continuity. Kind of catchy, right? Okay, Holy Trinity of continuity. So whenever we come across a continuity problem where they're asking us if a graph is continuous at a particular point, you must show those 3 items. Okay, we have to do that Holy Trinity. Does the point exist? Does the limit exist? And do they match?